All right, here we are. This is our last lecture. Crazy how time flies. So we're going to talk about, for our last lecture, stainless steel and aluminum. In chapter 9, we have stainless steels, if you've got your book. This is a little reminder of sort of the steel families as I've laid them out. So carbon steel is what we mainly, everything that we're welding in class pretty much. We talked about the alloy steels, quenched and tempered, chromoly. So now we're getting into the stainless steels, which are their own family here in the steel family. And to talk about stainless steels, we've got to talk about a little bit of metallurgy and a little bit of kind of more scientific understanding of steels here. So we're going to break it down to atoms. Atoms can bond with other atoms to form molecules. This is very simplified, obviously. And so most metals exist as a crystal structure or lattice of those atoms, how they've bonded together to form those molecules. So at a room temperature, without any welding or anything happening, they exist at this specific lattice-like structure. It's different for different steels, right? So these are the different examples of different lattice structures: cubic body-centered, cubic face-centered, and then hexagonal. So this will be, these little blue dots represent each different atom of, iron, carbon, whatever the other alloying elements are, etc. And then as you heat the material, this lattice structure changes, because basically heat equals energy. You put energy into atoms, they start moving around pretty much. And so that lattice structure, the way that they are kind of in a relationship with each other, will change with heat. So stainless steels have been manufactured to exist at very particular different crystal structures at room temperature. That's basically what gives them their stainlessness in essence. So now once you put heat into atoms, they move around. Then as they cool down, more different processes happen. So the metal begins to solidify, and this is even in a very small surface of just where that weld pool is, right? Because of course you've melted some of the base metal, so there's a small amount of liquid metal here that then is going to cool. So as this liquid metal solidifies, the crystal structures that we talked about join together, and then they form these bigger crystal type structures. And these are called dendrites, the little, like the pieces right here that are starting to join together. This is a big like liquid soup of metal, and then these little pieces are joining together as it solidifies and cools, and they get bigger and bigger and bigger until it's at its cooled state. So as it grows bigger and bigger and finally gets to its cooled state, you have these larger grains. And these this is like under a microscope. You would be able to see these kind of big shapes under a microscope. So this is the particular grain structure that this material has now. And the important thing to remember is the boundaries between these large grains. The grain boundaries are where things happen, and it's something that you have to kind of keep in mind. So just sort of things to hold in your head as we're talking about this, so you know what's really happening and what you're dealing with here. So now, stainless steels, a little bit more specifics about them. They are iron-based alloys, of course. They're still in the steel family, so they're still iron-based. To be stainless, it has to have a minimum of 10.5% chromium. It's a lot more chromium than would be in any kind of other alloy, or any other kind of steel. That's what pushes it into the family of stainless steels. And that chromium is what gives it the resistance to corrosion and oxidation, which is why it's stainless, why it's valuable. So within that stainless steel family, there's 5 different families underneath that. And that's what we're going to talk about: the austenitic, ferritic, martensitic, duplex, and precipitation hardening. And these stainless steels, these families are identified by their grain structure, which we just outlined. So they will have different grain structures, and that places them in the different families. This is another handy chart from this book that I like. You don't have to memorize it or anything, but it does kind of break down the composition of these different, more common stainless steels, if you're interested. So the first family, austenitic stainless steels. So austenite is a face-centered cubic structure. Remember the molecular, the atoms joining together and forming molecules. So austenitic stainless steel, the basic form of it is this face-centered cubic structure. And the austenitic stainless steel, of course, it gets more complicated. It's divided into two types. There's the 300 series and the 200 series. And the main elements of austenitic stainless steel, so the main alloying things that are in it, are chromium and nickel. So usually 16, 20%, 26% chromium, 8 to 24% nickel. The benefits of austenitic stainless steel, it's a very good corrosion resistance, and it's high strength and a high toughness. So austenitic stainless steel is the most common stainless steel out there. So if you come across a random scrap piece of stainless and you're not sure what it is, odds are that it is austenitic. That's a good first guess. Another thing you could do to check it is some of the stainless steels are magnetic and some are not. Austenitic stainless steel is non-magnetic. So, if you try to stick a magnet to it, it's going to have either maybe a very, very light pull, but usually no pull at all. And it can't be hardened by heat treatment. The non-magnetic aspect of it is related to that. So it can't be hardened by heat treatment, and it's non-magnetic. It's the main way to recognize it, because you can't see it visually unless you do like an etch test and look at it under microscopes and stuff. So the next family, the second most common stainless steel, is ferritic stainless steel. So ferrite, the main structure that makes it ferritic stainless steel, is a body-centered cubic structure. So you see the one atom in the middle here, as opposed to all of these on the face. This is the second most commonly used. The main alloying elements are chromium and carbon, small amounts of manganese and nickel. And the main types are 405, 409, 430, etc. So the 400 series is usually going to be a ferritic stainless steel. There's sometimes there's differences in there, but 200 and 300 series is austenitic, 400 is ferritic. So the ferritic stainless steel is ferritic at all temperatures. So even when you heat it up and it does move around, it will still maintain that basic body-centered cubic structure. It's not going to change. So that means, again, it can't be hardened by heat treatment. And this one is magnetic. An easy way to remember that, of course, is ferrite refers to iron. So ferritic stainless steel is the most iron-ish stainless steel. Therefore, it's the most magnetic. Austenitic is non-magnetic. Ferritic is magnetic. So if you can take a piece of stainless that you don't know what it is, test it with a magnet. If it's not magnetic, odds are it's austenitic. If it is magnetic, odds are it's ferritic. Then that kind of helps you gives you an idea of how to use it, how to deal with it, how to weld it, or whatever you're going to do with it. So next family, martensitic. So martensite is a body-centered tetragonal structure. Here's a sort of example here. You don't have to memorize all of these. It's just sort of to help you understand why these steels are different. The main alloying elements of martensitic stainless steel is chromium and carbon, these particular percentages and percentage ranges. So martensitic is also in the 400 series, as is ferritic. So it always gets more complicated than it needs to be, or than it could be. Martensitic stainless steel, the difficulty with it is it does have more of a tendency towards weld cracking during cooling. So that's why it's important to know what stainless steel you might be dealing with, because martensitic is going to be most prone to cracking. Then you would need to do preheating, interpass heating, and post heating perhaps, and control all of those things. Now, martensitic can be heat treated, so it can be hardened and annealed and stuff with heat. And it is also magnetic. So it's not as common as ferritic, but unfortunately ferritic stainless steel and martensitic stainless steel are magnetic. So again, it can be difficult to tell the difference just looking at them on the surface. Now, this gets to the even more complicated ones, duplex stainless steels. These are not terribly common, so you wouldn't necessarily encounter these sort of naturally. This would be something more specific where you'd be working with these particular stainless steels. Now, these are part ferritic and part austenitic. That's why duplex, like two. They solidify as 100% ferrite. That back here, the body-centered cubic structure. So they solidify like that, but half of the ferrite then transforms to austenite, the first one, during cooling. I don't know why. This is all metallurgy stuff. So this is, if you want to know more about this, then take Mike's metallurgy class because it's really good. But this is just kind of just scraping the surface of trying to understand some of this stuff. Now, the most common type of duplex stainless steel is type 2205, and it is also magnetic. Another one, precipitation hardening stainless steels. So precipitation hardening is a heat treatment that increases the yield strength of malleable materials. It's also called age hardening. It takes time. That's why it's called age hardening. And then, of course, this now is divided into martensitic, semi-austenitic, and austenitic precipitation hardening stainless steels. These are all of these different alloys are to get particular features that you're looking for. So the precipitation hardening steels are going to get high strength, high hardness, really good corrosion resistance, better than just your plain martensitic stainless steels. And then you improve the ductility, so the ability for it to be welded without cracking by doing tempering procedures. And they can be heat treated. So you have to know these things. If you're welding it, then you change the temper of it, and you have to reheat treat it to get it back to how it's supposed to be. The precipitation hardening stainless steels are labeled usually with the pH for precipitation hardening, so that is usually easy to tell. And if you are welding this, the electrode must match the base metal. So you have to make sure you're buying the correct electrode for the steel that you are welding. Speaking of electrodes, generally for all stainless steels, the electrodes need to be compatible with the base material. That doesn't mean that they have to be the exact same as the base material. It's just this chart will illustrate some of these base materials can be welded with the same alloy of electrode, right? So 308 alloy filler material can weld 301, 302, et cetera, all the way down the chart here. The reason why you have to use the correct alloy of electrode is you need to make sure that you have crack-resistant deposits. That's one of the biggest problems in stainless steel welding is these cracks. We talked about way back in the beginning, cracks are the worst discontinuity. It will always cause it to, you have to grind the whole thing out and re-weld it. So that's the biggest problem with stainless steel welding. Another thing that you can do with the electrodes is to enrich the alloy that you're working with. So to provide some other kind of, positive aspect, like more ductility, more corrosion resistance, or something else. So you can, think about how you're mixing the base material and the electrode because they're both, melting. And it's called enriching, where you could kind of improve what you're working with. You have to deal very carefully with stainless steel electrode wire because it is stainless and you want to keep it stainless. That's, again, the difficult part about welding stainless steel. It's just like really picky. You got to keep it pretty as clean as possible. I mean, medical grade clean would be ideal. So it has to be, the electrode wire has to be protected from contamination. That means you want to use a spool cover or store it in a container anytime it's not being used, especially, if you're working in a shop where you're also welding carbon steels and you might be grinding carbon steels and all that's going out into the air and can settle on your electrode wire because that would totally ruin it. That would make it not stainless anymore. So see, these are some of the more common electrodes. So you see the electrode and rod here, and then the 308, 308L, lower carbon. So these are the different alloys. That's what the electrode is telling you, what alloy it is. A little bit more about joint preparation. As I said, you have to have the right electrode for the base material you're using. You can do something sort of special in stainless steel called buttering, where you would take these two pieces of base metal are incompatible with each other. So you have to have a filler metal that is compatible with, this side and this side. So you'd fill this, you'd do it like a surfacing weld here with some kind of electrode that is compatible with this metal and with the main filling metal. And then on this side, you'd use a different alloy that's compatible with this base metal and also this main filler metal. And you'd surface that, and then you fill the whole thing in with your filler material. That's called buttering or cladding. So you can use for other types of joint preparation, you can use the standard welding, the weld joint designs, with your V groove, your J groove, your et cetera, et cetera. You would use a lot more. There would be much more opportunity, I guess, to use backing bars, which you might have seen at OCC. I know they use them in the TIG class, so especially for thin metals. But anytime you're welding stainless steel, like the more kind of tooling and protection and cleaning and et cetera you have for it, the better. So you have to really make sure the stuff is clean before you weld it. You can use a backing bar. And when you are cleaning anything that you're doing with the base metal, the weld, et cetera, you have to use tools that are only used for stainless steel. So if you use like this wire brush, for example, the bristles are made out of stainless steel. If you use that on your regular carbon steel weld and then went over to your stainless steel weld and tried to clean that off, you would be contaminating it with carbon transfer, because that stainless steel has picked up small particles of carbon and stuff from your carbon steel, and you're going to be scrubbing that into your stainless steel, so that can cause it to rust, to oxidize, and then you'd be ruining the whole point of the stainless steel. So you have to make sure you have tools only for stainless steel, and you keep them only for stainless steel. You'd want to keep them separate from your other tools in some kind of sealed container, preferably. So again, they're not sitting out and getting collecting the dust from grinding and stuff of carbon steels. Stainless is very picky. Tooling in general should be non-magnetic to prevent arc blow. It's another problem that's more of an issue with stainless steel, is the arc wanting to wander around. Important thing to remember is that stainless steel retains more heat than carbon steel. So tooling can be used strategically to remove the heat in order to reduce warpage and distortion and stuff. But you have to remember that stainless steel is going to it's going to warp more than your carbon steel is going to. So you have to take more precautions with stainless. And tooling can also be used to removing the heat, can help to avoid what's called carbide precipitation. So I talked about those grain boundaries. As it hardens, the dendrites sort of form together to form these larger grains. So there is carbon still in your stainless steel. Or there's the chromium in your stainless steel can move out from the mixture, the correct mixture in the grain, can move out to the boundaries and then form like places where it's going to crack more readily on those boundaries. So the chromium can precipitate, can like move out of the like main mixture and to form around the grain boundaries and cause more problems with cracking. So that's why heat can be such an issue with stainless steel. So tooling, if you use it strategically, you can help to kind of draw away some of that heat to prevent the whole piece that you're welding from getting as hot, to try to avoid that carbide precipitation, problems with cracking. Here is a picture of or an illustration rather, of the backing bar that I was talking about earlier. You can use a copper backing material, which helps remove the heat rapidly because copper is really conductive, and you have a machined like groove in it to allow the weld to fully penetrate. Or you can have a bar like this. So this would be like a copper one. You can have a bar like this that actually you can put a shielding gas into. It has these holes where the shielding gas will come up, and so that protects and covers the whole back side of your weld, so you can get a fully protected weld, preventing the oxidation there. There is also flux for stainless steel, and you mix it with alcohol or acetone, and you apply with a brush on the back side. So again, that still is just like protecting the back side from oxidation and stuff to get a good weld. So the main problem with stainless steel is that sensitization of the heat affected zone. Remember that the heat affected zone is everywhere around the weld area where the heat has traveled to. Because stainless steel is more conductive, that heat affected zone is going to be larger. It travels faster throughout the whole material. The sensitization is caused by the chromium carbide formation and carbide precipitation in the heat affected zone next to the weld. So it's basically like inconsistencies in that heat affected zone area, which can cause cracking there. This look of sugaring. You'll see it looks like burnt. You can see that there's a problem with it, and that the end result there is a breakdown of the chromium, decreased corrosion resistance in the end. So that's why you have to be really careful, because you're dealing with stainless steel, which the whole point of it is to be stainless. So if you've done something to disrupt that, then you're losing the whole property that you're trying the reason that you're using the stainless steel in the first place. So no preheating can be helpful. Minimizing the heat input is generally a good rule to follow. Anything you can do that minimizes the heat input is good. Hot cracking is a big problem with stainless steel. Again, minimizing the heat input. So lots of clamps that you can use. Do whatever you can to just keep that heat input as low as possible for stainless steel. Couple of tips: make sure if you're installing a wire into a system that has been used for carbon steel, you want to clean that inside of that system, blow it out with some compressed air or something. Make sure you're using the right electrode. You want the glass nozzle close to your work, so a little bit closer maybe than you would be used to for carbon steel. Generally use that push welding, forehand welding technique, especially for pulsed spray transfer or spray transfer modes. If you're doing short circuiting transfer, a slight kind of faster whipping motion can be helpful. Unfortunately, we don't have any stainless steel electrodes at OCC, so I can't really set anything up for you to test out, but this is all hopefully would be helpful to you later on if you do come into contact with some stainless. Use stringer beads, little or no weaving. Again, that reduces the heat input. For a multi-pass weld, make sure you brush it, clean it with that stainless steel brush that hasn't been used on any carbon steel. And don't leave craters at the end of the weld. That's sort of where you stop at the end of the weld quickly, and there's a little bit of like a concavity in there. You make sure that you fill that back in, because that kind of can create a weak point where with stainless steel it can be more prone to cracking there than it would be with carbon steel. You can use this runoff tab, so you weld past the main weld that you are working with, so you don't have any problems with the start and the stop. If you're using magnetic and non-magnetic types, you want to use a single bevel joint, and you want to weld in short circuit transfer mode, and you want to keep the electrode over the non-beveled edge as you're welding it. Again, control the amount of heat in the heat affected zone. Anything you can do to control the amount of heat is good, to reduce the amount of heat rather. All right, so that was our stainless steel kind of quick overview. Obviously, stainless as a whole is kind of its whole own separate animal. So that's just giving you some background information, so hopefully you can take that into a situation where you might need to weld stainless steel later on. And now we're going to talk about aluminum. So we just talked about stainless steel, which was in that steel family, which had a lot of other things in it. I'm going to go kind of bump one step up to ferrous versus non-ferrous. And we have mentioned this a little bit before. Ferrous contains iron, is magnetic, and has little corrosion resistance. So that will be all your steels. Everything in that steel family is ferrous. Non-ferrous means it does not contain iron. That's the main differentiation. Therefore, it's non-magnetic, and it tends to have more corrosion resistance. More malleable and usually lighter weight. So that's stuff like aluminum, which is what we're talking about today. Things like brass and bronze and copper and stuff like that. Non-ferrous, no iron. That's the main thing to remember. So aluminum is non-ferrous, but still easily welded with the GMOT process. It has high thermal conductivity. That means it gets hot quickly, and therefore good electrical conductivity. It has high ductility at sub-zero temperature. It's just not going to get too brittle and crack. Very lightweight and high corrosion resistance makes it very valuable. Non-sparking and non-toxic, which is, again, very valuable for some applications. And then no color change when heated. So that's the biggest thing that can kind of be really weird when you're starting to weld it. You won't see any color change happening, like none of that bright kind of orange or red color as you're welding. And as you see kind of the weld puddle and the base metal melting and stuff like that, there's none of that with aluminum, which could kind of be a little bit of a trip when you first start working with it. A little bit about the metallurgy of aluminum. It is the most common metallic element in the Earth's crust. Alloying elements that you add to it provide these specific characteristics to the pure aluminum. You do use pure aluminum, but it's much more common to use aluminum alloys. Major differences between welding steel and aluminum is that some alloys cannot be welded at all. Some aluminums cannot be welded. In the case of aluminum, the welds are weaker than the base material. It's not the case with steel. With steel, the weld is a very strong point. With aluminum, the weld joint is actually weaker. No matter how, even if it's a perfect weld, it's going to be slightly weaker than the base material without a weld. Excuse me. And only some aluminum alloys are heat treatable. It might surprise you, but some of them are actually heat treatable, so they're hardenable in a similar way that steel is. Pure aluminum melts at 1200 degrees Fahrenheit. Aluminum alloys are going to melt at 900 to 1200. So adding different alloying elements to them obviously changes the melting point. Here's the important part. The oxide film on aluminum melts at 3762 degrees Fahrenheit. So oxide film is like rust on steel. It forms on the surface of the aluminum during the manufacturing. It's good because it provides corrosion resistance, but it has to be removed before welding because of its higher melting temperature. If you just imagine that 3762 is like a thin layer on the surface, you're trying to weld it, your metal underneath melts at 900, so if you get your weld hot enough to melt the oxide film, you're going to just burn through the base metal. So that temperature difference would make it very difficult to weld. So you have to always remove that oxide film when you're welding aluminum. And unfortunately, you cannot see the oxide film. It's not like rust where it's a different color. And it basically starts forming on aluminum as soon as it's manufactured and kind of open to the air. So pretty much all aluminum has some kind of oxide film on it, and you do have to clean that off before welding in most cases. So the primary alloying elements for aluminum is pure aluminum, copper, manganese, silicon, magnesium, silicon, and zinc. There are two different families of aluminum. There's wrought aluminum or cast aluminum. So wrought aluminum is what we are working with for welding. It's metal that has been worked in its solid form. Cast aluminum is metal that's been melted and poured into a mold. So you can weld cast aluminum just like you can weld cast iron, but the processes are going to be different, and these are two different separate families of aluminum. So here's the different series designations for the wrought aluminum groups. Again, nothing you have to memorize here, just to give you a little taste of it. They're in the thousands as opposed to the hundreds like most stainless steels. And they're a little bit simpler designations, so just the one at the beginning of it tells you what the main alloying group it's in, which makes it a little bit easier to kind of get a rough idea of what you're working with. So the non-heat treatable wrought alloys are going to be the 1000, 3000, 5000, and some 4000 series. These are certain specific alloying elements that have been added for strengths. But they're not heat treatable. Some of them do harden when they're cold worked during manufacturing. So that's if they're hammered or squished or shaped or whatever while they're cold. They can get a little bit harder with that process. But you can't heat treat them. So the heat from the welding may reduce strength in that heat effective zone, and you can't bring that strength back. So it's just things that you have to think about and remember with these alloys. The heat-treatable alloys, 2,000, 6,000, 7,000, and again, some 4,000. So there's different heat-treated conditions, and then the weld zone may soften, and then you can heat-treat it, excuse me, to regain its pre-weld condition. So to get that strength back, basically. The heat-treatable wrought alloys are identified by temper designations and numbers. They'll tell you how they've been heat-treated or what they are that you're getting. Fabricated, annealed, strain hardened, and solution heat treated. Pardon me, are some of the main ones. So again, this is not a chart you have to memorize, just something that can be helpful. It tells you some of the different main designations that you might come across there for aluminum alloys. Now, the cast groups all have this decimal point in them. So they're similar looking, but they have a decimal point. So you should immediately be able to recognize if it's a cast or wrought aluminum, which is useful. Again, the number at the beginning tells you what alloy group it is, what the main alloying elements are. Cast alloys are commonly used for pump housing, engine frames, and motor bases, so things like that. You will encounter them. The main production methods are a sand mold, permanent mold, or die casting. They have that different numerical system to identify them, and some of them are heat treatable and some of them are not. They do have the same temper designations as wrought aluminum, those ones here. These are the temper designations. Some of them are heat treatable and some of them are not. If you wanted to get into all of the electrodes for aluminum alloys, it's in AWS A5.10. But these are the most common electrodes that I want you to try to remember. Is this electrode rod again, 4043. So this is the alloy that the electrode is made out of, and 5356. So if we go back just to illustrate my point to the chart. There we go. So the 4,000 that your alloy electrode that that is the most common is aluminum silicon. The 5,000 is aluminum magnesium. So again, aluminum is a little bit easier to tell something kind of right away at the beginning about what the electrode is that you're using. You don't have all the information, but you know the starting point easily, at least. And then this is again a further breakdown of the different filler metal and the different alloys that they can weld. So that's a really useful chart if you do get into aluminum. Another chart that is just sort of there for your information later on. It's like suggestions for what alloying elements to use for different base metals to get different things out of them, basically. Now, consideration when you're selecting your own electrode, the weld wire diameter is really important for aluminum because aluminum is so much softer. So it's much harder to feed through that whole gun, right? So you want to start with as thick of a wire diameter as possible. You have to think about your power source, what it's capable of welding, what mode you're using, what type of feeder equipment you're using, and then the type of welding gun, especially if you have a spool gun or a push-pull gun. We've talked about a couple of those. We've talked about both of those in a couple of lectures back. You have to think about the joint design, the position of the weld, and your ability to manipulate the gun, if you're in difficult positions or something. This is a term that you might come across when you're talking about aluminum that I wanted to define, dilution. So as I mentioned before, aluminum welds are weaker at the weld joint, the weld itself, than the base material. So to address this, try to fix this issue, aluminum electrodes are made of stronger alloys. So as an electrode melts, it mixes with the liquid base metal, as every weld does. So that includes the additional alloying elements in the electrode. So those additional alloying elements are now mixing in with the base metal, and this should lead to a weld that is as strong as the base metal because you've kind of over-strengthened the weld area in a way that hopefully just makes it even with the base metal. That process of the base metal mixing with the electrode is called dilution. So sometimes you might want more dilution, sometimes less. It's just another kind of aspect that you can control depending on which electrode you choose for your aluminum weld. Now, joint design is pretty similar to everything else we've talked about. Fillet welds, just pretty much the same. For a groove weld, butt joints, the center of the groove weld is going to shrink last. That can cause some problems with cracking in the center. That V groove or U groove can be useful to reduce dilution. We just talked about if you want to reduce dilution, you can choose a V groove or a U groove. If you have a square weld, you're going to increase the dilution. So again, depends on the alloy of aluminum that you're using, depends on what you're going to use that material for, whether or not you'd want more dilution or less dilution. But you can control that somewhat with the joint design, which is different for aluminum. Joint preparation, you can do plasma arc cutting, you can do carbon arc gouging, but these cause a really heavy aluminum oxide scale, which then has to be cleaned off. You cannot use the oxyacetylene process. Just doesn't work on aluminum. You have to clean the surfaces to bare metal because that aluminum oxide is not obvious. That's in most cases. You have to clean it. There are there's always some sort of exceptions to the general rules. So remove that heavy oxidation. You can use, files, discs, whatever. There are specific grinding wheels designed specifically for aluminum because it's so much softer. It will tend to clog up if you're using just a regular sandpaper sanding disc, it'll kind of clog it up really quickly. So there are specific ones designed for aluminum. Make sure your tools are designated for aluminum only, the same as with stainless steel. You could theoretically use your stainless steel tools on aluminum as well and vice versa, but it's better to have designated ones for aluminum, designated ones for stainless steel. If you have edges that have been prepared by shearing, you have to clean those edges, make sure there's no sharp spots or tears and ridges. You need it to be nice and smooth and consistent. You could file those edges to clean metal, again, to remove the oxide layer. And then tooling for aluminum, there's are definitely some similarities between aluminum and stainless steel. So you can use these backing bars. This is another example similar to the ones we talked about for stainless steel. All of it is preventing oxidation. So this has the gas comes back through these little holes and covers the back of the weld. For high quality ones, you have to purge it with argon or helium. For aluminum, a lot more tooling for aluminum is better, generally speaking. So in short circuiting mode, again, the mode that we use for our carbon steels at OCC, short circuit mode on aluminum is very difficult unless you are really control the electrode stick out. So that would mean being really careful with your distance away from the metal, basically. So usually you have to have an automatic welding operation for this, where there's a robot where it's set basically at a set height and it maintains that, very consistently. For spray transfer and pulse spray transfer, you use lower overall current levels, and you can use this in all thicknesses and positions. The welding gas for aluminum, argon is the main gas used, almost always used. You can add helium to it. Again, you get different qualities in your weld pool, more penetration, hotter weld pool, less porosity. And for your standard 1/2 to 5/8 diameter nozzle, a 25 to 40 CFH. So similar still to your carbon steels. If you are using a helium mixture, you have to use the higher end of this range, a higher CFH, because helium is lighter than air, so it's going to want to move off of the weld metal very quickly, so you kind of blast it with more helium in that case. Preheating for aluminum, it is doable and does help sometimes with reducing the heat that you have to do for the weld. It makes the welding speed faster. You don't want to heat it more than 300 degrees Fahrenheit for aluminum. You can check the temperature range with these guns, with like digital thermometers basically, or use these crayons, or there's different stickers that you can stick that'll change color when it gets to the temperature. But don't do it above 300. After preheating, so if you do a preheat, you use less current for the welding, which is good, and then the weld pool you have to know will be larger. So if you don't want, if there's something where you need to make sure there's a smaller weld pool, then you wouldn't do a preheat. Welding techniques for aluminum. You can do multi-pass welds. You have to, as with stainless steel, clean that completed weld before the next pass. Make sure you use a stainless steel brush, meaning the bristles are made out of stainless steel, not carbon steel. And then you do want to use an aluminum only brush if possible. You can use short circuit transfer or spray transfer. Use the forehand, the push technique for fillet and groove welds, because this will clean and etch the aluminum as you weld. Craters and cracking are a real big problem, or can be a big problem in aluminum, especially the craters. When the cross section, if you chop that weld in half, is thin or concave, there can be more cracking happening in that area. So you want to avoid stopping the weld at the end of the joint, just like stopping just there and having these craters forming, see? Again, that same with stainless steel, that concavity. So before stopping, keep the same gun angle, finish up your weld, and then move back into the end of the weld to kind of fill in that crater, and then you won't have that problem that could lead to cracking at the end. You can also use runoff tabs, these short pieces at the ends of the weld, so that you start your weld here. If there's any problems, it's not on the main weld body, and you end it over here. So if you have any craters or weird stuff, it's still, again, it's not on the main weld. For a slot plug or spot plug or slot welding, it's the same technique as carbon and stainless steels. Now, I told you, I was mentioning that with aluminum, the wire is so much softer, so it can be much more of a problem with feeding the whole thing. So you can have that bird nesting happen a lot faster and a lot easier, because that wire is so much weaker. It's not as strong to push through the whole thing. Usually it occurs when the aluminum electrode melts or adheres to the contact tip, and then it's stopping right there, and then you try to keep welding, and then it backs up in the drive rollers. Because aluminum's melting point is low, this is why it happens so often. And in this case, the electrode material and the contact tip are both non-ferrous, so they can weld to each other a lot easier than when you're using a carbon steel electrode and a non-ferrous contact tip. They don't tend to stick together in the same way. So that's another reason why aluminum is a little bit more of a problem. And you have the bird nesting, which you've all encountered in carbon steel too, probably. But it just happens a lot more often in aluminum. So to avoid it, you want to start with a lower voltage setting, and then adjust to a little bit higher as your metal heats up and as you're welding. And then have a higher wire feed setting, so that wire is more prone to pushing out of the contact tip faster, a little less chance of adhering to the contact tip. And then adjust it lower, when you're kind of dialing it in. Have short arc times, as short of arc times as possible. Closely watch that wire supply, and clean and maintain it. Make sure that you keep your gun like long and free of any loops or kinks. It's just aluminum, but it's a little bit more difficult, but it's still weldable. So there's our last lecture, aluminum and stainless steel, getting into some more complicated stuff there. And if you have any questions, of course, feel free to ask me. We will be, of course, meeting in class, depending on when you're watching this, if we've already met or we're going to meet on Thursday, and then I'll see you in class on Friday, of course. Have a great week. If you have any questions, send me an email. Bye.